Proxima Centauri is right next door in cosmic terms, and still so far that our fastest probes today would need tens of thousands of years to get there. To turn that into a human-scale mission, you need drives pushing a ship to a fraction of light speed. Shielding that can take decades of cosmic gunfire, and a crew willing to bet their lives on a planet orbiting a violent red dwarf that might already be dead. This video walks you through that entire journey, from the first bolt in orbit to the first close-up look at Proxima b, using only real physics and the hard engineering it demands. Right now, Proxima Centauri sits about 4.24 light-years away. 1 light-year is around 9.5 trillion kilometers, so the gap between you and Proxima is roughly 40 trillion kilometers, about 25 trillion miles. To get a sense of how extreme that is, take normal human speeds. Our fastest deep space probes cover maybe 17 kilometers per second. A car on a highway does around 30 meters per second. If you somehow drove that car straight toward Proxima and never stopped, you'd need on the order of 50 million years to arrive. That's longer than humans have existed as a species. This is why a Proxima mission isn't just a bigger Apollo. It's a jump into a distance regime where everything you know from planetary missions breaks. But distance is only the first shock. The second shock is what you're actually going to see when you get there, because Proxima Centauri is not a second sun waiting to greet you. Proxima is a red dwarf. In basic numbers, it has about 12% of the sun's mass and roughly 14% of the sun's radius. If the sun were a big sphere, Proxima is more like a small ball nested inside it. Its total power output is less than 1% of the sun's. In simple terms, it is tiny and dim. If you stood at Earth's distance from Proxima, you would freeze. So any planet that wants Earth-like temperatures has to orbit very close in. Instead of 150 million kilometers like Earth, you're talking just a few million kilometers from the star, a small fraction of Mercury's distance. In that tight orbit, a year lasts days, not months. You might think a small dim star would be calm and quiet. Proxima is the opposite. It is a flare star. Its magnetic field twists and snaps, and when it does, it releases violent bursts of high-energy radiation. These flares can be hundreds of times more intense in X-rays and ultraviolet light than the sun's usual flares. For any nearby planet, that means repeated blasts that can heat and erode the upper atmosphere and slam the surface with charged particles. So you are aiming at a star that is small, faint, and unstable. That sounds like a poor candidate for a peaceful, life-friendly system. So why is this still the #1 interstellar target? Because Proxima is not alone. It has planets, and we already have evidence for them from real data, not just theory. Astronomers have watched Proxima Centauri very carefully using a method called radial velocity. They track tiny back and forth shifts in the star's spectrum as it moves toward and away from us. Those shifts come from the gravity of orbiting planets tugging on the star. From that wobble signal, one planet shows up clearly, Proxima b. Proxima b has a minimum mass around 1.2 to 1.3 times Earth's mass. That probably makes it an Earth-like or slightly heavier rocky planet, not a gas giant. It orbits the star in roughly 11.2 days, at a distance where our average energy from the star is in the right range for liquid water. That puts it in the famous habitable zone. There's more. The same data point to a second planet, Proxima c, farther out, most likely a super-Earth or mini-Neptune on a much wider orbit. And there is also a candidate inner planet, Proxima d, completing an orbit in about 5 days even closer to the star. The details are still being refined, but the key point stands. Proxima Centauri has a compact planetary system, with at least one world that could, in principle, have surface temperatures that allow liquid water. So your destination is not just a single red star in a void, it is a mini-system with multiple planets, one of them sitting in the right energy band to be interesting. That sounds like good news, but there is a big catch hidden inside that word habitable. The standard habitable zone idea only cares about distance and starlight. It asks, is the energy arriving at the top of the atmosphere in the right range to keep water from instantly freezing or boiling. It does not ask what the star's flares are doing to the atmosphere. It does not ask how the planet spins. Around a star like Proxima, those missing details matter a lot. Proxima b orbits at about 0.05 astronomical units, around 5% of the Earth-Sun distance. At that distance, the gravitational pull on the planet's near side and far side is different enough that over time the star can force the planet into tidal locking. That means one hemisphere always faces the star and one hemisphere always faces away, just like one side of the moon always faces Earth. If that's true, you get a permanent day side and a permanent night side. The day side is constantly illuminated and heated. The night side never sees the star at all. Without an atmosphere, the day side could bake while the night side drops to near absolute zero. Add Proxima's strong flares to that picture, and the day side atmosphere is under continuous stress from X-rays and charged particles that can strip gas away into space. The only way to get a stable, mild region is if the planet has a thick enough atmosphere and maybe oceans to move heat around efficiently. Air and water would need to redistribute energy from the day hemisphere to the night hemisphere. Some climate models suggest you could get a band of tolerable temperatures around the terminator zone, that ring between day and night where the star always sits low on the horizon. Other models suggest the atmosphere might collapse or be lost over time. So Proxima b could be a world with a narrow strip of habitable territory under weird skies. Or it could be a bare rock with a thin or missing atmosphere, blasted by flares and stripped by the stellar wind. Either answer is important. This planet is a direct test of whether habitable zone around a red dwarf really means habitable for life, or just not frozen in theory. That leads to the main strategic question. With a violent little star and a planet that might be half-baked and half-frozen, why risk turning your first interstellar mission into a decades-long trip to a possible dead end? The answer is simple and brutal. Proxima is the closest star system you can reach. Every meter per second of speed you can wrestle from real physics gives you more science per year if you point it at this system instead of a farther one. If you somehow build a ship that can cruise at a significant fraction of light speed, Proxima is where the numbers start to work at all. At around 0.2 times the speed of light, the trip from Earth's frame is about 2 decades. At 0.1, it's 4 decades. That's still within a human lifetime. Go to a star twice as far and everything stretches. And this is not just about one star. Most stars in the Milky Way are red dwarfs like Proxima. If Proxima's planets turn out to be stable, and maybe even support some form of atmosphere or life, then suddenly tens of billions of similar stars become serious candidates for habitable worlds. If Proxima b is dead and stripped, that suggests a huge fraction of the galaxy's habitable zones are misleading. One mission can move a huge part of the exoplanet debate from theory to direct measurement. So when you pick Proxima Centauri as your first interstellar target, you are not just picking the nearest light in the sky. You are making a high-stakes bet about what kind of galaxy you live in and whether planets around red dwarfs can really be homes. But all of that science only matters if you can actually get there in less than geological time. And right now, with our fastest probes needing tens of thousands of years, that sounds impossible. So the next problem hits you. How do you cross 4.24 light years of space fast enough for a human crew or even a meaningful probe to arrive within a working lifetime? How long are you actually willing to wait for a result? Because at our current speeds, the answer for Proxima Centauri is longer than human civilization has even existed. Start with the basic number. 1 light year is about 9.5 trillion kilometers, roughly 5.9 trillion miles. Proxima sits 4.24 light years away, so the gap is around 40 trillion kilometers, about 25 trillion miles. That is the hard physical distance between you and the nearest other star. Now drop in our fastest real hardware. Voyager 1, launched in 1977, is moving at about 17 kilometers per second relative to the Sun, around 38,000 miles per hour. That's incredibly fast by normal standards. At that speed, crossing the distance to Proxima would take on the order of 70,000 to 80,000 years. Agriculture started less than 15,000 years ago. You're talking multiple times the entire length of recorded human history just for one one-way trip by a small probe. So the first blunt truth is this: with today's deep space speeds, Proxima Centauri is not a destination. It's essentially geological time away. That's the pain hidden inside the nice simple label 4.24 light years. So where do you even start cutting that number down? The obvious move is to say, fine, just build a bigger rocket. That's where the physics slams the door. Chemical rockets are what we use now. The most advanced ones we've flown, like the RS-25 engines on the space shuttle, and the engines planned for the Space Launch System, push hot exhaust out the back at around 4.5 kilometers per second, a bit under 3 miles per second. With careful staging and clever paths, that lets you get a spacecraft up to maybe a few tens of kilometers per second relative to the Sun. For missions inside the solar system, that's workable. For Mars, Jupiter, even Pluto, you can stretch chemical systems and gravity assists and eventually get there. But Proxima is different. To cross 4.24 light years in something close to a human lifetime, you need cruise speeds of roughly 1/10 the speed of light. Around 30,000 kilometers per second, about 19 million miles per hour. That's about 3 orders of magnitude faster than what chemical engines can reasonably give you. The problem isn't optimism or engineering talent. It's the basic math of rockets. To get huge speed increases from a low-speed exhaust, you have to carry insane amounts of propellant. Double the speed you want, and the mass ratio explodes. By the time you talk about tens of thousands of kilometers per second with chemical exhaust, your ship is essentially an absurd mountain of fuel with a tiny payload. And even then, the numbers barely work on paper. In practice, chemical rockets are simply dead for interstellar journeys. They are not weak, they are irrelevant. So if normal rockets are out, what counts as fast enough to even justify trying? Where is the minimum viable starship speed? Take that same 4.24 light-year distance and start plugging in higher cruise speeds, ignoring acceleration and braking for a moment. At 1/10 light speed, about 0.1 c, the trip takes around 42 years in the frame of someone watching from Earth. At 0.2 c, about 1/5 light speed, you're down to roughly 21 years. That's the span of a single human career. You could in principle launch a mission in your 20s and still be alive when the signal comes back with first light images of Proxima b. If you settle for 0.05 c, about 1/20th light speed, now you're at around 85 years one way. That basically turns into a lifetime mission for someone born after launch, or forces you into suspended animation or multi-generation ships. Go slower than that and the story shifts. It's no longer you go to Proxima, it becomes your descendants or your frozen body finishes what you started. So distance itself pushes you into the relativistic regime. You don't get to stay in the comfort zone of traditional rocketry. If you want a mission that completes in a few decades, you're automatically talking about a significant fraction of light speed. But once you start cranking speed up like that, another question hits. How much energy are you really loading into this thing? Kinetic energy climbs extremely fast with speed. By the time your ship is doing 0.1 c, 1/10 light speed, each kilogram of its mass carries on the order of hundreds of trillions of joules of kinetic energy. For rough intuition, that's similar to the energy released by about 100 million tons of TNT per 1,000 tons of spacecraft. A serious crewed starship could easily mass thousands of tons once you add structure, life support, reactors, and shielding. So now you're talking about total kinetic energies in the range of a few % of all the energy human civilization uses in a year today dumped into one vehicle. And that's just the cruise energy. You have to spend something similar to accelerate, and again to slow down, unless you use clever tricks with sails and fields. Your engine is no longer more powerful than a Saturn V. It's something that has to operate at civilization-scale energy levels. That's the cliff you stand on. If you move too slowly, the mission is pointless. If you move fast enough to be useful, the energy bill looks like something only an advanced global civilization can pay. Does that push this whole thing into pure science fiction? Or is there any sign that we can actually reach those speeds with real physics? This is where projects like Breakthrough Starshot come in. Starshot is not a crewed mission, and it won't look like a classic rocket. The idea is to use extremely powerful ground-based lasers, together pushing out power measured in gigawatts to drive very lightweight spacecraft attached to tiny reflective sails. Each ship in that concept could weigh just a few grams. The sail is only meters across. The lasers in the solar system hammer the sail for minutes, maybe hours, and push the probe up to around 0.2 C, about 20% of light speed. At that speed, the probe reaches Proxima in about 20 years. We do not have the lasers, the huge phased array optics, or the ultra light sails for this yet. It's a massive engineering lift. But here's the key point. The physics piece is standard. This is just light pressure, electromagnetism, and special relativity working together. There's no warp drive, no new physics, nothing that contradicts what we already test in labs. It's brutal engineering, not magic. So the gap between you and Proxima is not some abstract, untouchable number anymore. It's a hard engineering problem pinned down by 3 facts. Chemical rockets fail completely, useful missions demand speeds of at least a tenth of light speed, and at those speeds, you are handling energies on the scale of entire nations. The next question is the one that really decides everything. If chemical engines are out, what real propulsion systems are left that can obey known physics, handle civilization-scale power, and still push a starship towards 0.1 C or beyond? You know you need something like a tenth of light speed or more. The next question is simple and brutal. What engine can actually do that without breaking physics, and without turning your ship into a useless block of fuel? Start with why normal rockets fail. The key number engineers watch is called specific impulse. In plain language, it tells you how efficiently a rocket turns propellant into push. Higher specific impulse means you get more change in speed for each kilogram of fuel you throw out the back. Chemical rockets, even the best ones we've flown, top out around 450 seconds of specific impulse in vacuum. That's what the space shuttle's main engines managed. With that level of performance, you can stack stages and play clever trajectory games and reach a few tens of kilometers per second, good enough for the solar system. But interstellar travel is not asking for a few tens of kilometers per second. To hit 0.1 times the speed of light, you are talking about tens of thousands of kilometers per second. When you plug those numbers into the rocket math, keeping exhaust speed fixed at a few kilometers per second, the fuel requirement explodes. The rocket equation basically tells you, to get those huge speeds with chemical exhaust, the mass of propellant has to be so extreme that your ship becomes almost all tank and very little payload. So chemistry doesn't just struggle, it drops completely out of the game. For Proxima, chemical rockets are as useful as a bicycle on a transocean flight. If normal combustion is out, the next step people always ask about is obvious. Can nuclear power save you? Nuclear thermal rockets are the first rung on that ladder. Instead of burning hydrogen with oxygen, you run liquid hydrogen through a very hot nuclear reactor and blast it out the nozzle. Because the hydrogen gets much hotter than in a chemical flame, it moves faster, and your specific impulse roughly doubles to around 800 to 900 seconds. That is a clear improvement. For missions to Mars or the outer planets, this could cut travel time and boost payloads. But even double the efficiency is nowhere close to what you need for interstellar work. You are still stuck with exhaust speeds of just a few kilometers per second and facing the same rocket equation wall when you ask for tens of thousands of kilometers per second of ship speed. So engineers pushed further and came up with nuclear pulse ideas. The most famous is Project Orion. You literally drop small nuclear bombs out of the back of the ship and detonate them behind a thick metal plate attached to shock absorbers. Each blast slams the plate, which transfers momentum to the ship. It sounds insane, but on paper the numbers are strong. Because nuclear explosions pack far more energy per kilogram than chemical fuel, Orion concepts can, in theory, push a large ship to many thousands or even tens of thousands of kilometers per second. Later, fusion-driven concepts like Project Daedalus explored using small fusion explosions instead of fission bombs. In those designs, pellets of fusion fuel are ignited in rapid sequence, producing a high-speed plasma exhaust. Now you're finally in the right range, big enough delta V to talk seriously about nearby stars. The problems are obvious: detonating thousands of nuclear devices near a spacecraft, handling the shock, dealing with fallout if you ever lighted off near Earth, and building structures that can survive that repeated punishment. None of that is solved. But nuclear pulse systems are the first class of engines that even reach the right ballpark for interstellar speeds. So you might ask, instead of exploding nuclear devices behind the ship, can you just run on the same reaction that powers stars and use it in a more controlled way? That is the idea behind fusion rockets. Fusion combines light nuclei like deuterium and tritium, or deuterium and helium-3, into heavier nuclei and releases huge energy. Per kilogram of fuel, fusion can deliver orders of magnitude more energy than chemical reactions. That translates in principle to very high exhaust velocities and therefore very high specific impulses, in the tens of thousands of seconds or beyond. The classic engineering study here is the Daedalus design from the 1970s. It was a two-stage fusion ship weighing tens of thousands of tons. The plan was to accelerate to about 12% of light speed and reach Barnard's star in roughly 50 years. It would use electron beams to ignite tiny fuel pellets many times per second, each one creating a fusion micro-explosion whose plasma exhaust pushes the vehicle. We still cannot run a controlled, power-producing fusion reactor on Earth for more than short bursts. We definitely cannot ignite pellets at high repetition rates and direct the exhaust neatly. But the physics itself is not in doubt. If you can solve the enormous engineering problems around fuel handling, ignition and shielding, a fusion drive can, in theory, push a starship into the 0.1 C range. That's the good news. The bad news is that fusion ships are gigantic, complex machines. You need mining of rare fuel like helium-3, huge magnetic or inertial confinement hardware, and heavy shielding around both crew and engines. These are not sleek, tiny craft. They are more like mobile power stations that happen to have a drive nozzle. If even that feels too heavy, the next question people ask is there any ultimate fuel where you get the maximum possible energy from every kilogram you carry? That's where antimatter comes in. For normal fuels, you release only a small fraction of the stored mass as usable energy. In antimatter annihilation, when a particle meets its antiparticle, most of their combined mass is converted directly into energy. In realistic engine designs, you could potentially turn around half of that total mass into directed kinetic energy in your exhaust. That's an efficiency nothing else can touch. On paper, antimatter engines look like the dream solution. You carry very little fuel and you get enormous push, but in real life we run into a wall even faster than with fusion. We can currently make tiny amounts of antimatter in particle accelerators, nanograms per year maybe. A serious starship drive would need kilograms. Producing that much would cost absurd amounts of energy and time. Then there is storage. Antimatter cannot touch normal matter without annihilating. So you'd need perfect magnetic or electric traps running for decades without failure. Any leak would be catastrophic. Right now we can hold very small numbers of antiparticles for short periods. Scaling that to starship levels is far beyond anything we know how to build. So antimatter sits there as the theoretical endgame. It tells you where the ceiling is. You cannot get more energy per unit mass than all the mass turned into energy, because of the relationship between mass and energy. But it does not give you a practical engine anytime soon. That leaves one more big idea. If hauling your energy source with you makes everything huge, dangerous, and expensive, can you leave the heavy hardware behind and push the ship from home? Beamed sails take that approach. Instead of a rocket engine, you give your craft a large, very light sail made of reflective material. Back in the solar system, you build massive laser or microwave arrays that pump power into a tight beam. That beam hits the sail, reflects, and transfers momentum to the craft. No propellant is carried on board. The engine stays at home as a giant power and optics system. We've already tested the basic sail idea on a small scale. Japan's Icaros mission and the Planetary Society's lightsail too use sunlight for push, not lasers, but they proved thin film sails can control a spacecraft's orbit. Now stretch that to the extreme. Instead of sunlight, use multi-gigawatt lasers and ultra-thin reflective materials. For gram-scale probes, serious studies show you could push them to around 0.2 C in minutes to hours of continuous beaming. For crewed ships, you can't keep the mass that low. A human-rated vehicle plus life support and shielding will be many orders of magnitude heavier, but the same concept scales in principle. Use beamed power to do the heavy lifting during the acceleration phase, then switch to onboard nuclear or fusion systems later, especially for braking near Proxima. You trade huge onboard fuel tanks for even bigger infrastructure back home. Giant ground-based or orbital arrays with extreme pointing accuracy, plus the problem of how to slow down once you're out of reach of the beam. The core pattern is now clear. Every realistic Proxima engine involves a painful trade. Chemical is out. Nuclear thermal helps inside the solar system, but not for stars. Nuclear pulse and fusion can get you close to 0.1 C, but demand enormous, complex machines. Antimatter sets the ultimate efficiency limit, but is far beyond our production abilities. Beamed sails cut onboard mass, but require gigantic power systems at home and new methods to brake at the target. Before you ever design a habitat module or think about the view from a Proxima window, you have to pick which of these brutal options you're actually going to bet your civilization on. And as soon as you pick one, another hard problem lands in your lap. Every kilogram you add to that design makes all of this even worse. How big can your starship be before it collapses under its own demands? Because every kilogram you add has to be slammed up to a huge fraction of light speed, and the bill for doing that grows fast. This is the tyranny of mass. Say you have a probe that weighs 10 tons. To push that to 0.1 times the speed of light, you need a certain amount of engine power, fuel and time. Double the dry mass to 20 tons and keep the same propulsion system, and either your travel time stretches out or you simply never reach your target speed. To keep the same performance, you have to scale your drive system, your fuel and your structure. The whole design inflates. Realistic studies for serious interstellar probes usually end up in the tens to low hundreds of tons range. That's already larger than most spacecraft we've ever flown. Once you add a human crew, life support, spin habitats for artificial gravity, radiation shielding, food production, and large engines, the mass shoots into the thousands or even tens of thousands of tons. Think several international space stations bolted together, then covered in armour, then strapped to a fusion drive. And remember, every ton you add doesn't just sit there. It needs to be accelerated up to maybe 30,000 kilometers per second and then slowed down again near Proxima. So the very first design rule is harsh. If you can leave it off the ship, you do. If you can make it lighter, you must. And then, even after you cut everything you can, one huge category of mass refuses to go away. Radiation protection. Outside Earth's magnetic shield, space is filled with charged particles and high-energy cosmic rays. On the International Space Station, astronauts, protected by both Earth's field and some structure, get around 80 to 160 millisieverts of radiation in a 6-month stay. That already raises their long-term cancer risk in a measurable way. Now take a mission that lasts 20, 30, 40 years in deep space with no planetary shields, no quick emergency return and a constant rain of cosmic rays. If you sent people out there with minimal protection, the accumulated dose would be lethal. You're not dealing with a minor health concern, you're dealing with survival. To cut galactic cosmic ray exposure to safer levels, you need material between your crew and the incoming radiation. Engineers often talk about grams per square centimetre of shielding. Roughly tens of grams per square centimetre starts to make a big difference. That could be several centimetres of aluminum, or on the order of a metre of water or other hydrogen-rich material wrapped around the habitat. Now apply that to a real structure. If your living section has hundreds of square metres of surface area, think a rotating ring tens of metres across. Wrapping it in that much material easily adds hundreds of tons of mass. Water, polyethylene, regolith from asteroids, layered metals, whatever you pick, it's heavy. You might tuck water tanks, fuel and food stores into the walls to make them do double duty, but the basic problem stays. A long-duration crewed starship needs a radiation storm cellar at minimum, and ideally a generally shielded habitat. That's non-negotiable. And radiation from distant sources is only one side. The other side is the stuff you hit. At normal interplanetary speeds, micrometeoroids and dust grains are a known risk, but we already know how to shield against them. At 0.1 C, 10% light speed, the same dust grains become serious weapons. A tiny particle with the mass of a grain of sand slamming into your hull at that speed carries energy comparable to an explosive. You won't see it coming in time to dodge. You will hit many such grains over light years of travel. The interstellar medium might have, on average, about 1 atom per cubic centimetre, with roughly 1% of that mass in dust. That sounds like almost nothing, but stretch it over trillions of kilometres and your ship's forward face will be peppered with countless impacts. Left unprotected, critical systems up front would erode, crack or fail, so you need real armour in the flight direction. Current spacecraft use what are called Whipple shields, a thin outer plate that breaks and vaporizes an incoming particle so that the energy spreads out before it hits the main wall. For a starship, you might stack many such layers separated by gaps to slow and disperse debris. You might put a thick, replaceable bumper up front that slowly ablates away over the journey. On top of that, you can add active defences, radar or lidar to detect larger rocks, lasers to vaporize or push them aside, magnetic fields to deflect charged dust and ions. All of this hardware lives on the forward edge, which means all of it adds mass where mass already hurts you the most. So now you have a ship that is big, shielded against radiation, armoured against dust, and powered by an exotic engine. The next failure mode is ugly but simple. What happens when things just break over time? Voyager 1 and 2 have lasted nearly half a century, not because they are futuristic, but because they were designed to be conservative and robust. Low-power electronics, simple systems, lots of redundancy. Even then, they are slowly aging out. Your Proxima ship needs to operate for decades, mostly alone, in a much harsher environment and with far more complexity. Every major system, propulsion pumps, valves, guidance sensors, gyroscopes, communication arrays, life support must have backups. In many cases, you want not just one backup, but several. You also need the ability to repair or replace parts during the mission, either by the crew or by robotic maintenance units. This isn't just a belt and suspenders mindset. Over the full mission duration, the total operating hours of your machinery will exceed the typical lifetime of most components. If you don't include redundancy and repair, the math says critical systems will fail before you finish the trip, so you accept more mass for extra hardware, extra spares, extra tools, because the alternative is losing the ship halfway in the dark with no rescue. All of that hardware, from engines to shields to life support, needs constant power. But as you leave the inner solar system, your easiest power source dies off. Solar power gets weaker with distance. Double your distance from the sun, and the light intensity drops by a factor of 4. By the time you reach 100 astronomical units, about 100 times Earth's distance from the sun, sunlight is down to 1/10,000th of what you get near Earth. In practical terms, solar panels the size of a football field would barely generate anything. Beyond that, it's basically dark. So an interstellar ship has to run on nuclear power. That can be radioisotope generators like Voyager uses, which turn the decay heat from radioactive material into electricity. It can be fission reactors, like very compact, long-lived nuclear power plants. Or, if your propulsion is fusion, you might tap that same system for onboard power. Whatever you pick has to meet a brutal set of conditions. It must survive launch, vibration, vacuum, deep cold and radiation. It must run for decades with no external maintenance base. It must handle varying loads as the ship switches between cruise, science operations and emergency modes. And it must do this while also feeding power-hungry systems like communication lasers, life support and active shielding. At that point, your ship has stopped being just a vehicle. It has become a small, closed industrial ecosystem, a power plant, factory, habitat and shield all bolted together and thrown between the stars. Every kilogram you add to make it safer or more redundant hits you again in propulsion costs, shield size and reactor size. So the pressure ramps up. You need a ship heavy enough to keep humans alive and systems running for decades, but light enough that your chosen engine can actually push it to 0.1 C or more. Balancing those two demands is not optional. If you get it wrong, you either kill the crew slowly in a fragile tin can, or you design a perfect city in space that no engine can ever move, and you haven't even left Earth's neighborhood yet. So the next hard step is obvious. How do you actually assemble this monster, get it out of Earth's gravity well, and then break free of the sun with enough speed left over to even call this an interstellar journey? How do you actually get a multi-thousand-ton starship off Earth if no single rocket on the planet can lift it? The answer is, you don't. You build it above your head. A realistic Proxima ship is far beyond a one-shot Saturn V-style launch. Instead, you break it into modules, engine blocks, fuel tanks, habitat rings, shield segments, radiator panels, reactors, communication masts. Each of those rides to low Earth orbit on heavy-lift rockets, tens or even hundreds of launches over years. We've already done a small-scale version of this. The International Space Station is about 400 tons and took dozens of launches and years of assembly. Your Starship could easily be 10 times that mass or more. So you are now talking about a permanent construction site in orbit. Robot arms, tug vehicles, maybe even dedicated orbital shipyard platforms that grab arriving modules, dock them, weld connections, run cabling and check seals. Every subsystem needs full testing in orbit. Life support runs for months before anyone commits to leaving. Spin habitats are slowly brought up to artificial gravity and monitored for vibrations and structural stress. Reactors are activated in carefully controlled steps, far enough from Earth that a failure doesn't drop radioactive debris back into the atmosphere. Only when the entire stack, engines, tanks, shields, habitats, power, comms, has behaved for a long checkout period, do you even think about the next step? And that next step is not just fire the engines. Before you can go interstellar, you have to do something more basic. Climb out of the gravity wells you live in right now. Leaving low Earth orbit is only the first part. From the surface, Earth's escape speed is about 11.2 kilometers per second, around 25,000 miles per hour. From low orbit, you're already moving at about 7.8 kilometers per second, so you need roughly another 3.2 kilometers per second to be fully free of Earth's gravity. But even when you've escaped Earth, you're still deep in the Sun's gravity. Earth orbits the Sun at about 30 kilometers per second, roughly 67,000 miles per hour. To go from bound to the Sun to on a path that never comes back, you need to raise your solar speed enough to beat the Sun's grip. From Earth's distance, that escape speed is around 42 kilometers per second if you started from rest, because you're already moving with Earth. The details are more subtle, but the key point is, getting free of the Sun takes a serious extra push, and for Proxima, that's still just the warm-up. Your interstellar injection burn has to stack on top of all this, pushing your hyperbolic excess speed, the speed you still have after completely escaping the Sun, into the tens of thousands of kilometers per second. That's where the 0.1 C or 0.2 C numbers live. Everything up to solar escape is basically noise compared to the speed you actually need. You don't want to waste any of your precious propellant on gravity wells if you can avoid it. That's where gravity assists and a trick called the Oberth maneuver come in. We already use flybys around planets to reshape spacecraft trajectories. Voyagers used Jupiter and Saturn to gain speed for free, relative to the Sun. New Horizons stole a boost from Jupiter on the way to Pluto. For your Starship, similar assists around Jupiter or other massive worlds can help, especially to bend your path inward toward the Sun for the next move. The Oberth effect is simple in concept. The faster you're moving when you fire your engines, the more useful energy you get from each bit of propellant. So the best place to do a huge burn is at the lowest point of your orbit, where you're moving fastest. For a starship, that probably means diving very close to the sun, whipping around at extreme speed, and hammering the main drive right at that closest approach. In practice, that could have meant swinging into a perihelion far inside Mercury's orbit, where sunlight is dozens of times stronger than at Earth. Your ship will need serious heat shielding and active cooling just to avoid cooking. Radiators might have to retract, protective shutters close over sensitive equipment, and propellant might double as a thermal buffer. Then, during those intense minutes or hours near perihelion, your fusion or nuclear pulse drive lights up and pause on delta V when it counts the most. Once that burn is over, you cross a line you cannot easily uncross. That's the commitment burn. The commitment burn is when your ship stops being something that could, in theory, return to the solar system with a big enough course correction and becomes a projectile whose path won't bend back for tens of thousands of years. Depending on your engine type, that main acceleration phase might be a short, violent, high-thrust event near the sun, or months of steady push if you have a continuous thrust fusion or beamed sail system. Either way, when it ends, your velocity relative to the sun is locked in. Minor course corrections are still possible with small thrusters, enough to hit a narrow target zone around Proxima instead of missing by billions of kilometers. But turning around is effectively impossible. You simply don't have the propellant to kill that much speed and then rebuild it in the opposite direction. From that moment, the mission is one way in every meaningful sense. There is no return capsule waiting, no rescue trajectory that makes sense, no "we changed our mind, come home." The commitment burn is where you trade all remaining flexibility for the speed you need. The ship, the crew, and decades of planning are now locked onto a single thin path through interstellar space. After that, something strange happens to your sense of scale. The solar system, which once looked enormous, collapses into a short opening chapter. Look at what we've done so far. Voyager 2 took about 12 years to reach Neptune, around 30 astronomical units from the Sun. New Horizons, one of the fastest craft we've ever launched, took about 9 years to reach Pluto at roughly 32 astronomical units. Those timescales set our current mental picture. The outer planets are far and slow to reach. A ship targeting 0.1c lives in a completely different regime. Once it finishes its acceleration phase and settles into cruise, 30 astronomical units, about 4.5 billion kilometers or 2.8 billion miles, becomes a short hop. Even if you account for a gradual acceleration period and some time spent climbing out of the sun's gravity well, you're talking months from Earth orbit to crossing Neptune's distance, not close to a decade. From the crew's point of view, the solar system flashes past. Jupiter and Saturn are quick milestones on the way out, not permanent destinations. Uranus and Neptune are blips on the navigation plot. The Kuiper Belt and scattered icy bodies that took New Horizons nearly a decade to reach become a brief phase filed under early mission operations. By the time you reach the edge of the Sun's major planet zone, most of your old instincts about distance and time are already broken. The real journey is only starting. Ahead of you is not empty nothing, but the thin, dangerous environment where the Sun's influence finally fades and raw interstellar space begins. So the next question is simple and serious. What actually happens when you leave the Sun's protective bubble and cross the true boundary into the galaxy's environment itself? You might think leaving the solar system means crossing some neat border like a fence line. It doesn't. But there is a real physical boundary out there, and your ship punches through it in days instead of decades. The sun is not just a light in the sky, it's a machine constantly blowing material outward. It throws off a stream of charged particles called the solar wind, racing outward at hundreds of kilometers per second, hundreds of thousands of miles per hour. That wind slams into the thin gas between stars and carves out a giant bubble around the sun. That bubble is the heliosphere. Inside the heliosphere, the solar wind dominates. Its particles and magnetic field shape the local environment. At some distance, the wind slows from supersonic to subsonic as it pushes into interstellar material. That slowdown region is the termination shock. In the direction Voyager 1 went, That's roughly 80 to 100 astronomical units from the Sun. 1 astronomical unit is the Earth-Sun distance, about 150 million kilometers or 93 million miles, so you're already around 12 to 15 billion kilometers out there. Farther out is the heliopause, where the outward pressure of the solar wind balances the inward pressure of the interstellar medium. In Voyager 1's direction, that's around 120 astronomical units, roughly 18 billion kilometers, more than 11 billion miles from the Sun. Inside that surface, you still live in the Sun's bubble. Outside it, you're in the galaxy's environment, where the gas and magnetic field belong to the local interstellar cloud, not to the Sun. So how sure are we that this bubble and its boundary are real, and not just a textbook sketch? That's where Voyager earns its place in your story. Voyager 1, launched in 1977, spent decades plodding outward. In 2012, about 35 years after launch, its instruments registered a set of changes. The density of surrounding plasma jumped, the direction of the magnetic field shifted, and the flux of high-energy galactic cosmic rays increased sharply. The solar wind particles it had been measuring dropped off. Those signatures match exactly what you'd expect when crossing from solar-dominated space into interstellar plasma. Voyager 2, heading out on a different path, repeated the story in 2018. Different trajectory, different timing, same pattern, a distinct boundary with a change in environment on both sides. That's hard evidence that the heliopause is not just theory. It's a real frontier that human hardware has already sampled, with numbers and timestamps, not guesses. But now take that 35-year crawl and put it next to your Starship Sprint. Voyager needed decades to reach about 120 astronomical units. A ship that has already ramped up to around 0.1 times the speed of light is in a completely different league. Once your main acceleration phase is over and you're at cruise, 120 astronomical units is only about 18 billion kilometers. At roughly 30,000 kilometers per second, about 19 million miles per hour, that distance is less than a week of travel. Depending on your exact trajectory and how long you spend climbing out from the Sun, you can hit the heliopause days after your main burn, not in mid-career. So for you, the edge of the solar system is not a goal decades away. It's a quick milestone on the mission timeline. You finish your commitment burn run through final checks, and less than a week later, you cross the heliopause. That doesn't mean the crossing is unimportant. Inside the heliosphere, the Sun's magnetic field and solar wind blunt some of the galactic cosmic rays. Outside that shield is gone. The flux of very high-energy particles is higher. Your radiation dose rate ticks up. Any magnetic sails or plasma shields you're using now have to interact with the interstellar plasma instead of solar wind. Your comm systems and sensors see a different background. The environment you designed for inside the bubble is not exactly the one you get outside it. If the space beyond the heliopause is still almost empty, can you just treat it as a slightly rougher vacuum and move on? At low speeds maybe, at a significant fraction of the light speed, not really. The Sun is currently moving through a region called the local interstellar cloud. The average particle density out there is on the order of 1/10 of an atom per cubic centimetre. The magnetic field strength is a few microgauss, millions of times weaker than a refrigerator magnet. Those numbers sound tiny, but at 0.1 C, your ship is ploughing through that medium at around 30,000 kilometers per second. In your frame, neutral atoms and ions are ramming into your forward shields with extreme kinetic energy. Even a low-density plasma can generate serious heating, sputtering and charge buildup on your hull. The magnetic field is weak, but you are moving through it very fast. That motion can induce electric fields and currents in your structure. It can interact with any loops of current you're using for magnetic sails or plasma shields. If you rely on a magsail concept for braking later, the exact density and ionization level of the interstellar medium and the field geometry directly affect how much drag you can generate. None of this is purely academic, it feeds straight into how thick your forward armour must be, how you ground and bond your structure, and how your plasma and magnetic systems are tuned. So if you're forced to cross this boundary anyway, and your survival depends on understanding both sides, Why not turn the whole thing into a major science experiment? Your ship is not just a vehicle, it's a moving laboratory. As you rush outward, you carry instruments far better than Voyager's. High-resolution magnetometers, particle detectors that can sort ions and electrons by energy, plasma wave antennas, neutral atom imagers, maybe even tiny deployable probes to map the structure off your main track. Inside the heliosphere, you map how the solar wind thins with distance, how its magnetic field lines stretch and twist, how cosmic rays are modulated by solar cycles. At the termination shock, you watch how a supersonic wind turns subsonic. At the heliopause, you trace exactly where the sun's influence ends and the galaxy's medium takes over. You measure how sharp or fuzzy that boundary really is, whether it ripples, whether it shifts over time. Once you're outside, you track the properties of the local interstellar cloud directly. The exact density of hydrogen and helium, the temperature, the small-scale turbulence, the background magnetic field, the detailed spectrum of cosmic rays. Over time, your line of travel becomes a high-precision slice through the galaxy's environment, not just a single-point reading like Voyager gave us. That data feeds straight back into engineering for every future mission. It tells the next generation exactly how much shielding they need, how their mag sails will behave, how fast their sensors will degrade, and how accurate their models of the heliosphere and local cloud really are. It also rewrites our basic understanding of how stellar winds carve bubbles in the interstellar medium, and how those bubbles overlap and interact across the galaxy. But crossing the heliopause is only the start of your exposure. The heliosphere was a diluted, magnetized cushion between you and the galaxy. Beyond it, you're dealing with the full interstellar medium for light years. Gas, dust, and fields that are thin by everyday standards, but brutal at your speed. So the next problem is direct and dangerous. For the entire rest of the journey, what exactly are you flying through? And how do you keep that almost nothing from acting like high-speed shrapnel that can tear your ship apart? You keep hearing that space is a vacuum, but for a ship going to Proxima, almost empty is not good enough. At 0.1 times the speed of light, that thin haze between stars turns into a continuous threat. Between stars and the Milky Way's disk, the average density is about 1 atom per cubic centimetre. Where the Sun is right now, in the local interstellar cloud, it's a bit lower, maybe a few tenths of a particle per cubic centimetre. Most of that is hydrogen, with some helium and trace heavier elements. Mixed into that gas is dust, tiny grains from well below a micron in size up to pebble-scale particles. In normal life, that would be nothing. In interstellar flight, that's your environment for years. So the basic picture is simple. As you leave the heliosphere, you enter a region that is not empty, just extremely diffuse, but at the speed you're aiming for, even a few atoms per cubic centimetre, and a sprinkle of dust become important. The question is not, is there anything there? It's, how much damage does that small amount do when you hit it at tens of thousands of kilometres per second? Start with dust. At everyday spacecraft speeds, dust is a design problem but not an existential threat. At 0.1 C, around 30,000 kilometres per second, about 19 million miles per hour, it's a different story. Take a grain of dust with the mass of a grain of sand. At that speed, its kinetic energy is in the range of tens of megajoules. That's similar to the energy released by a small military explosive. Even much smaller grains, far below what your eyes could see, pack serious energy because kinetic energy grows quickly with speed. A steady stream of those hitting your forward structure will chew into anything that isn't heavily protected. You will not dodge them. You will not see most of them in time. Over several light years, the number of impacts is not maybe 1 or 2. Integrated over years of travel, you are guaranteed a large number of hits. Even if each grain is tiny, the accumulated effect on unprotected surfaces is erosion, cracks, and structural weakening. So your design cannot treat dust as background noise. You must assume constant bombardment in the forward direction and build in sacrificial shielding that you expect to lose. Simulations and studies suggest you need multiple layers of material up front that can be gradually ablated and replaced or simply oversized so that losing a chunk over the mission still leaves adequate protection. That's where shield architecture becomes as important as the engine. Current spacecraft already use Whipple shields, a thin outer layer that takes the initial hit, vaporizes the micrometeoroid, and spreads the impact energy over a larger area before it reaches the main wall. For a starship at 0.1 C, you scale that concept way up. You might fly with a thick, solid bumper shield made of metal, ceramic, or composite materials mounted ahead of the main hull. Behind that, you stack separated layers of additional shielding that catch debris and plasma from the first impact. On top of that, some concepts add a several meter thick artificial cloud of gas, ice particles, or very fine dust released in front of the ship. Incoming grains first slam into that cloud, lose energy, fragment, and only then reach the hard shield. That cloud has to be continuously replenished from onboard stores, which means more mass and more plumbing. But without something like it, your forward armour has to be overbuilt to insane levels. And remember, it's not just solid dust. The gas itself, hydrogen and helium atoms, also hits your bow and any exposed structures, gradually eroding surfaces and creating charge buildup. For larger objects, anything from big grains to actual rocks, you add active systems. Radar or LiDAR can scan ahead for larger pieces. If you have time, lasers can heat and vaporize or gently push them off your collision path. Magnetic fields can deflect charged dust and ions, but none of these will catch everything, especially very small, fast-moving grains. They are an extra layer on top of passive shields, not a replacement. So you are ploughing through a medium that tries to sandblast your hull and knock holes in your ship every second. That sounds purely hostile. Is there anything useful you can do with this material, or is it only a problem? Back in the 1960s, physicist Robert Bussard proposed an idea that turned the interstellar medium into fuel. The Bussard ramjet concept uses a huge magnetic scoop in front of the ship to collect interstellar hydrogen and funnel it into a fusion reactor. In theory, you run a star in reverse, collect gas from space, fuse it, throw the fusion products out the back as exhaust, and accelerate indefinitely without carrying much fuel. In practice, simple versions of this idea don't work well. At realistic field strengths and densities, the drag from pushing against the interstellar gas and field can exceed the thrust you get from fusing it. You slow yourself down instead of speeding up, but the core thought is still interesting. The medium you're flying through is both resistance and potential resource. Modern variants talk about using smaller magnetic scoops not as the primary fuel source, but as a supplement. You might gather a trickle of hydrogen to feed a fusion reactor that mainly runs on onboard fuel, or you might use the collected material as extra reaction mass, heated by onboard power rather than fusion of that same gas. Either way, the thin gas between stars becomes part of your power and propulsion budget, instead of only something that hits your hull. On paper, these hybrid concepts are still early and full of engineering challenges, building and stabilizing massive magnetic fields, dealing with drag, handling plasma instabilities. But the direction is clear. At the speed you're targeting, you can't ignore the interstellar medium. It fights you and it can, in principle, help you. And while all of this is happening, your science team is busy treating the entire journey as one long, continuous experiment on the galaxy itself. As you move between stars, your instruments don't just measure impacts and radiation levels for safety. They also watch how the interstellar gas and dust absorb and emit light. Neutral hydrogen produces a famous radio signal at 21 centimeters wavelength. Molecules like carbon monoxide CO, cyanide CN, and other sequeurs leave distinct fingerprints in different parts of the spectrum. By recording these signals at high resolution at every step of your path, you map the temperature, density, chemical makeup, and motion of the gas you're passing through. Doppler shifts in those lines tell you how the gas is moving relative to you. Changes in intensity and width tell you about turbulence and clumping. Combined with magnetic field measurements and cosmic ray spectra, you turn your straight-line trip into a detailed cross-section through a piece of the Milky Way's disk. From Earth, we mostly see this material integrated along long lines of sight. From your ship, you watch it change point by point, so the empty space between here and Proxima turns out to be a complex, thin, dangerous medium. It eats at your shields, charges your hull, messes with your fields, and if you design things right, can feed your reactors and your science teams at the same time. Now add one more layer. You're doing all of this at a speed where classical intuition starts to slip. Time on the ship and time on Earth stop matching perfectly. Starlight warps into a forward cone. Radiation from ahead gets harder and more intense just because of your motion. At that point, it's not just the environment that changes. The basic rules of how you experience space and time begin to shift into the relativistic regime, and that becomes a daily practical problem, not a classroom thought experiment. How fast can you go before time itself stops matching what everyone back home thinks is normal? On a Proxima run, that's not a thought experiment, it's your daily schedule. Once you start talking about 0.1, 0.2, 0.5 times the speed of light, relativity stops being classroom weirdness and becomes basic mission planning. The key idea is simple. As your speed gets close to light speed, time on your ship runs at a different rate than time for people watching you from Earth. At about 0.1 seek, 10% of light speed, this effect is present but small. Your time dilation factor is around 1.005. In plain words, for every year that passes on Earth, about 11.5 months pass for you. That's only about 0.5% difference. You'd barely notice it over a decade. Push harder. At around half light speed, your factor jumps to roughly 1.15. Now, for every year on the ship, about 1.15 years pass on Earth. Over a 20-year mission, people back home age by about 23 years while you age 20. Still close, but you start to feel the gap. Go extreme. At about 90% light speed, that factor is a bit more than 2. That means clocks on your ship tick a little more than twice as slowly as clocks on Earth. For a 4.24 light-year trip at 0.9 c, Earth sees roughly 4.75 years go by from departure to arrival, not counting acceleration and braking. On board, you experience only about 2 years of cruising. The harder you push toward light speed, the more your mission timeline splits into 2 different stories, one on Earth, one on the ship. So you're forced to ask a sharp question. How much time are you willing to lose relative to humanity to cut down the trip from your own point of view? Even at more modest starship speeds, like 0.2 c, the mismatch is small on paper but very real. At around 1/5 the speed of light, your time dilation factor is about 1.02. That's only a 2% effect. Take the 21-year Earth frame trip we talked about earlier for 0.2 c to Proxima. On the ship, you would experience around 20.6 years instead of 21. You personally only gain back a few months over 2 decades. But now zoom out. Across a network of missions over many decades, those small offsets pile up. A probe launch 10 years after you, going slightly faster, might arrive not long after you do, even though its launch date is clearly later on Earth. A second-generation starship leaving with better engines might overtake slower craft en route. Updates from Earth about new physics or better maps will always arrive years late in your frame, and the people sending them will age more than you by the time you even read their messages. The moment you lock in a relativistic cruise speed, you desynchronize from Earth's history. Culture and technology back home continue on their own line. Your line is tilted relative to that, shifted by the way special relativity handles time. For mission control, you're outship there for 21 years. For your bones, your organs, and your onboard clocks, you're out there for slightly less. Neither view is wrong. They're just different descriptions of the same reality. So if clocks and calendars become slippery, how do you even know exactly where you are out in deep space without GPS or familiar landmarks? Near Earth, we use GPS satellites in medium Earth orbit. They are tens of thousands of kilometers away, and they only cover a small bubble around our planet. They are useless once you're far into the solar system and completely irrelevant at Proxima. You need a navigation system that works when the nearest human-made object is trillions of kilometers away. That's where pulsars come in. Pulsars are neutron stars, collapsed stellar cores, with intense magnetic fields. They spin rapidly, sometimes hundreds of times per second, and shoot out beams of radio or X-ray radiation from their magnetic poles. As they spin, those beams sweep past us like cosmic lighthouses, producing extremely regular pulses. Some pulsars keep time more steadily than atomic clocks. You can catalogue the pulse patterns and positions of many pulsars across the sky. Then your ship carries X-ray or radio detectors that pick up those pulses. By measuring tiny differences in pulse arrival times from different pulsars and comparing them to the known patterns, your nav computer can solve for your exact position and velocity in three-dimensional space. NASA has already tested this in a basic way with the sextant experiment on the International Space Station, getting position accuracy on the order of a few kilometers. Scale that up with better detectors and more processing power, and you have a galaxy-scale navigation grid that works anywhere, including near Proxima Centauri. So now you know you're at the right place at the right time, your time. But your view of the universe is no longer the same as the view from Earth. At high fractions of light speed, starlight from ahead doesn't come at you evenly from all directions. Because of your motion, it gets squashed into a cone in front of the ship, an effect called aberration. Stars that would be off to the side in the sky for a stationary observer appear shifted forward. More of the universe crowds into your front view. On top of that, light from ahead is blue shifted. That means its wavelength gets compressed. Radio waves slide toward microwaves. Infrared creeps into visible light, pushes toward ultraviolet, and so on. The cosmic microwave background, which looks like cold microwaves from Earth, becomes hotter, more energetic radiation in your forward direction. Interstellar hydrogen in front of you looks like a more intense headwind of particles and radiation. Behind you, the opposite happens. The sky is dimmer and red-shifted. From your perspective, the universe becomes uneven. The forward direction is not just brighter, it's harsher. That has direct design consequences. You need thicker radiation shielding in the nose than in the tail. Your sensors facing forward must be hardened and sometimes filtered to avoid being overwhelmed by shifted, intensified radiation. You might plan observations off to the side or behind the ship for sensitive instruments that can't handle the forward glare. So now, relativity is not just messing with your clocks. It's reshaping your entire radiation environment. The faster you go, the more the cosmos in front of you turns into a bright, energetic and dangerous cone. Given all of this, you'd better be very sure our understanding of relativity is correct before you bet $1 billion mission and human lives on it. The good news is that special relativity has passed every test we've thrown at it so far. Particle accelerators, GPS corrections, atomic clocks flown on airplanes, satellites in orbit. The bad news, if you're a theorist hoping for surprises, is that all those tests cover limited regimes. Small scales, short durations, and mostly near Earth. A Proxima mission gives you a completely new way to test these ideas. You launch with a network of ultra-precise clocks on board, synchronized with clocks on Earth to tiny fractions of a second. You track your velocity profile during acceleration, cruise, and braking. You log the tick rate of your onboard clocks and the frequencies of signals you send and receive. Over decades, you collect a huge data set of how time and frequency actually behave for a macroscopic object, your entire ship, moving at a fixed fraction of a light speed over light years of distance. When you arrive at Proxima and later when data gets back to Earth, scientists can compare every prediction from special relativity with what really happened, down to very fine precision. If there is any tiny deviation, maybe 1 part in a quadrillion, it will show up as a mismatch between expected and observed timestamps or signal frequencies. If it matches perfectly, you've confirmed Einstein's picture in a regime we've never accessed before. If it doesn't, you've just cracked open the foundations of physics. So on this journey, relativity is not a background theory. It is your clock, your navigation, your radiation environment, and your science target, all at once. You can't opt out of it. You travel at a fraction of light speed, so you live inside its rules. And while all of that is bending your sense of time and direction, one old simple problem never leaves. You still have a human body, built for 1G and Earth's protection, stuck in a metal tube for decades in deep space. The next question is unavoidable. What actually happens to your biology your mind, and your tiny onboard society when you try to live, work, and not fall apart on a ship that never comes back? How much radiation can a human body really take before the mission stops being science and starts being a long, slow, medical experiment on you? On the International Space Station, astronauts spend about 6 months at a time in low Earth orbit. There, they're still partly protected by Earth's magnetic field and by some structure around them. Even so, they pick up around 80 to 160 millisieverts of radiation in that period. That already gives a noticeable bump in lifetime cancer risk. Agencies manage this by limiting total career dose and carefully screening. Now stretch that out. A Proxima mission means 20 to 40 years in deep space outside the magnetosphere, with higher galactic cosmic ray levels and occasional solar storms, plus an extra boost once you're past the heliosphere. Even with good shielding, the cumulative dose is going to be far beyond anything any human has ever taken on purpose, so your options are not great. 1. You over-engineer shielding, thick layers of water, plastic, maybe even hydrogen-rich materials or magnetic fields, to knock down as much radiation as you can. That costs mass, which makes the ship harder to push. 2. You organise the ship so the crew spends as much time as possible in a central storm shelter region, surrounded by tanks and supplies that add extra protection. You rotate people through the best yielded zones, track individual doses, and treat exposure like a budget. 3. You accept that this crew will have a higher lifetime risk and compensate with aggressive monitoring, constant blood tests, advanced imaging, onboard diagnostics, early interventions, maybe even preventive surgeries or gene-based treatments. In practice, you do all 3. You build in as much passive shielding as your propulsion can handle. You design a core safe room and sleeping quarters at the centre of that protection. You equip the medical bay like a small hospital with advanced scanners and lab tools, and you accept that everyone who signs up is taking a bigger gamble with their health than any astronaut before them. But surviving radiation is only part of staying alive. You also have to eat, breathe, drink, and not drown in your own waste for decades without a single resupply ship from Earth. Right now, the ISS recycles most of its water and a lot of its air, but it still depends on regular cargo missions for food, spare parts, and some supplies. Your Proxima ship will not have that. Once you leave, your grocery store is what you launch with and what you can grow on board. That means building a closed ecosystem that actually works long term, something we have never fully demonstrated. Attempts on Earth like Biosphere 2 in Arizona showed how hard this is. Systems drift, carbon dioxide builds up in weird ways, microbes take over parts of the loop, nutrient balances shift and plants struggle. Psychological stress rises when people feel trapped in an artificial environment that sometimes fights back. Your ship has to do the same basic tasks but better. Grow food at scale, recycle water with very low loss, scrub and regenerate oxygen, break down waste into useful inputs, and keep trace chemicals and microbes under control. You need bioreactors, algae or plant tanks, soil or hydroponic systems, and robust monitoring of gas composition and nutrient flows. You also need ways to reset parts of the system if they drift too far, sterilize a bioreactor, replace a batch of growing medium, seed new microbial communities, without breaking the whole loop. From an engineering point of view, this is at least as hard as the engine. A glitch in the drive means you might miss a science goal or lose some speed. A glitch in your life support loop means you lose the crew, so you treat the habitat like a living machine, sensors everywhere, redundancy in each link of the chain, and enough onboard manufacturing to replace filters, tubing, and hardware as they age. On top of that, your body is not built for drifting in zero-G forever. We already know that humans in microgravity lose bone density, especially in the hips and spine. They lose muscle mass even with hours of exercise per day. Fluids shift in the body leading to eye problems. 6 months on the ISS causes clear, measurable changes that doctors have to manage. Decades in microgravity would be catastrophic. Fragile bones, weak muscles, damaged vision, cardiovascular problems. That's simply not acceptable for a mission like this. so a serious starship design almost has to include artificial gravity. The easiest method with known physics is rotation. Build a ring or two large modules on a tether and spin them so that the floor pushes on your feet the way Earth's gravity does. At the right rotation rate and radius, you get about 1 g at the rim. We've never flown a big rotating habitat in space. Your ship might be the first. That brings a pile of new questions. How big does the ring need to be for people to feel comfortable and not get dizzy from the spin? How do you handle the forces on the structure from constant rotation and occasional course corrections? How do you move between spinning and non-spinning parts of the ship safely? You also need to test in real life whether long-term spin gravity actually prevents the worst health problems. Maybe you find that 0.7 g or 0.8 g is enough. Maybe you discover weird inner ear effects or subtle long-term issues. Your mission becomes the first real experiment in how much gravity does a human really need, and you're running that experiment millions of kilometers from the nearest hospital. Even if you solve radiation, air, water, food, and gravity, one hard problem stays: your crew are not robots. They are people locked in a tube for decades, with the nearest help years of light time away. We already see how isolation stresses people in Antarctic stations, submarines and long-haul missions. Small teams, confined spaces, limited privacy, repeated routines, and long periods without outside contact all push on human psychology. On a Proxima mission, those stressors are amplified. When something goes wrong, no rescue ship is coming. If you argue with someone, you will still see them every day for the next 20 years. So you don't just pick the best scientists and pilots. You pick people who can live together under pressure for a long time. You train them not just in technical skills, but in conflict resolution, counselling and group decision-making. You build clear governance structures: who decides what, how disagreements are handled, how leadership rotates or stays stable. You design rituals and schedules that break monotony: regular weekends, celebrations tied to mission milestones, time-off zones in the habitat. You also design communication with Earth with this in mind. There will be long delays, years, not minutes, once you're near Proxima. But early in the mission, when delays are shorter, you can stream messages, entertainment, even live or near-live conversations. Over time, that link becomes more one-way and more symbolic. Your onboard culture will drift from Earth's. New slang, new traditions, new shared history. You're not just moving a crew, you're seeding an isolated micro-culture and hoping it stays stable enough and sane enough to finish the job. All of this effort raises a sharp question. Is there any way to reduce the time people actually spend awake and exposed on the ship? If you had real suspended animation, the answer would be yes. Put the crew into controlled hypothermia or some form of metabolic slowdown so their cells tick over at a fraction of normal speed. They sleep through most of the journey, waking only for key phases like departure, mid-course checks, and arrival. That would cut their accumulated radiation dose, reduce the psychological strain, and lower demand on food and life support while they're down. Right now, true long-term cryosleep is science fiction, but we already use short-term therapeutic hypothermia in medicine and see natural hibernation in animals. Somewhere between those lies the possibility of multi-month or multi-year sleep cycles, may be supported by controlled cooling and careful rewarming. Even partial success, slowing metabolism for months at a time, rotating hibernation shifts, could be a major advantage. Parallel to that, you can push biology in the other direction. Make the crew more resistant instead of just trying to protect fragile baseline humans. Gene therapies that enhance DNA repair, drugs that boost antioxidant systems, engineered gut microbes that help handle stress and unusual diets, even pre-planned stem cell treatments to repair radiation damage. You start treating the human body not as a fixed passenger, but as an adjustable system you tune for deep space. The Proxima mission becomes the forcing function. It takes keep astronauts alive for a year and upgrades it to keep people alive, functional and sane for decades in an artificial world. That pressure drives radiation medicine, closed-loop life support, artificial gravity design, and human factors engineering forward faster than any low Earth orbit program ever could. But even if you solve the human side, one harsh fact remains. Your starship is also a living system in its own way, full of parts that wear out, and it has to keep itself running for as long as your crew does, without a dockyard or a warehouse of spares. So the next problem is just as unforgiving. How do you build a machine that can detect its own failures, repair itself and manufacture its own replacement parts, all while crossing light years of hostile space? How do you keep a machine alive when the mission is as long as or longer than the expected lifetime of almost every part inside it? Every component on your ship has a mean time between failures, MTBF. A pump might be rated for tens of thousands of hours. A high-end processor might effectively last for years under normal use. Even deep space probes are usually designed for mission lengths of a few decades at most. A Proxima mission, counting assembly, checkout, cruise, braking and arrival operations, can easily stretch to 30 or 40 years. Some parts will run almost the entire time. Statistically, that means something simple. Most critical systems will fail at some point. Not might, will. Your power converters, thruster valves, gyroscopes, star trackers, data buses, and storage drives will age, wear, and occasionally die. If you design this ship as if everything will just work for the entire journey, you're building a failure. So you have to design from day one with the assumption that breakdowns are normal. You don't ask, how do we avoid failures? You ask, when systems fail, how do we keep going? That means redundancy. Primary, backup, second backup. It means modular systems that can be physically swapped out. It means constant health monitoring so you catch components degrading before they take down the whole chain. But you hit a hard limit. You can't just pack a second and third copy of every valve, pump, reaction wheel, circuit board and antenna unless you want the ship's mass to explode. You need another strategy. If you can't carry spares for everything, can you make spares for almost anything? That pushes you toward in-flight manufacturing. Instead of crates full of specific replacement parts, you bring raw materials and tools that can reshape those materials into what you need. That means metal stock, polymers, electronic feedstock, and recycling systems to break down failed components and reuse their material. Add 3D printers for plastics and metals, precision machine tools, maybe even systems that can print circuit boards or simple chips. Wrap all of that with fleets of maintenance robots and drones that can move around the ship, inspect damage, and do repairs where humans can't safely go. In practice, you're flying a compact factory. When a pump body cracks, you don't pull an identical pump off a shelf, you print a new housing, reuse the old motor if it's still good, and bolt it back together. When a radiator panel gets eroded by dust hits, you send robots to cut away the worst sections, swap in new material and reseal it. Over years, the as-flown ship drifts away from the as-built blueprint as repairs and upgrades accumulate. You also update designs on the fly. Maybe early in the mission you notice that a certain joint wears out faster than expected. You redesign that part in software, print a stronger version, and roll it out across the ship. That loop, detect, redesign, manufacture, install, becomes normal operations. The price you pay is complexity and mass for all the manufacturing gear, but you gain the ability to cope with unknowns that no ground test could reveal. All of that, though, relies on one more thing. The brains running the ship have to be just as adaptable as the hardware, without becoming unpredictable. Over decades, your software will not survive in its original state. Cosmic rays will flip bits in memory. Sensors will drift and need new calibration models. Hardware will be patched, rerouted, or replaced. Communication protocols with Earth will evolve. New algorithms and bug fixes will arrive years after you launch. You cannot freeze your codebase on day 1 and expect it to still be correct on day 7,000. So onboard control systems, up to and including AI, need to update themselves. They must learn from sensor data, adjust parameters, integrate patches received from Earth, and sometimes even rewrite or replace entire subsystems. At the same time, they must stay aligned with mission goals and safety rules that cannot change casually. That's a serious open problem. You don't want a system that optimizes away safety margins because it learned that running hotter or skipping checks gets more data. You don't want maintenance bots that subtly change priorities because of an error in a learning update. You need strict guardrails, verification systems, and perhaps multiple independent AIs cross-checking each other and human oversight, at least while light time delays are still manageable. In reality, you will end up with a hierarchy: low-level real-time control loops that are simple and robust, mid-level planning systems that can adapt to hardware changes, and high-level mission logic that rarely changes and is heavily protected. Any self-modification has to go through layers of checking, maybe even simulated sandboxes on board, before it touches live systems. While all this software and hardware is evolving, one boring-sounding problem is quietly trying to kill you: heat. Space is hold in the sense that the background environment doesn't give you much heat, but your ship constantly generates waste heat from reactors, engines, electronics, life support, and humans. All that heat has to go somewhere. In space, you can't just blow air over a radiator into the atmosphere. You only have radiation. You throw infrared light off large radiating surfaces. In low Earth orbit, thermal management is serious but manageable. Between the stars, with megawatts of reactor and engine waste heat, it becomes central. You need big radiators, often spanning tens or hundreds of square meters, to dump that energy. At high cruise speed, anything that sticks out sideways is exposed to dust impacts and particle erosion. Simple flat wings of radiator panels become targets, so radiator design becomes a balancing act. You want enough surface area to glow away heat, but shapes and angles that reduce the exposed cross-section to oncoming dust. You might tuck radiators into shadowed regions behind your main shield, or use looped configurations where hot coolant runs through channels in armoured structures. Materials must handle decades of heating and cooling cycles, radiation and impact damage without cracking or degrading too far. If thermal control fails, nothing else matters. Electronics overheat and fry, life support breaks down, reactors trip offline or melt components. So temperature sensors, coolant pumps, and radiator control systems become just as critical as navigation or propulsion. Even if you manage all of this, repair, software, heat, there was still one question you can't dodge. What happens when the ship as a whole starts to age out? What if, despite all your planning, things decay faster than expected? You need end-of-life plans. One option is a safe park mode. If the mission is clearly not going to make it, maybe a major engine system is beyond repair, or radiation damage to core structures is too severe, the ship could shut down most active systems, point its antenna at Earth as best it can, and drift in interstellar space while still sending health and status data as long as power remains. Another option is a planned shutdown sequence triggered from Earth. Ground controllers, looking at decades of telemetry, might decide that pushing further risks uncontrolled failures. They could send a series of commands, knowing they'll arrive years later, to wind the mission down in a controlled way. Dump remaining data, power down reactors, safe critical systems, maybe leave some instruments running as long as the power budget allows. Even a failed arrival still gives you something huge: hard data on how a complex spacecraft actually ages over 30 or 40 years in deep space. What broke first? What wore out slower than expected? Which shielding strategies worked and which didn't? That information feeds straight into the next generation of starships. But all of this assumes one more crucial piece: that you can keep talking to Earth at all as you cross 4+ light years, and that those slow delay conversations are enough to guide patches, upgrades, and decisions over decades. So the next challenge is obvious and unforgiving. How do you run a mission when every question you ask home takes more than 8 years to get a full answer? How do you run a mission when every question you ask takes almost a decade to get an answer? Radio waves and laser beams move at light speed, but light speed is not instant over 4.24 light years. From your ship near Proxima to Earth, a message takes about 4.24 years to arrive. Any reply from Earth takes another 4.24 years to come back. So if you send We see something weird. What should we do? At Proxima, you get guidance roughly 8.5 years later, assuming instant response on the ground. That delay kills the idea of real-time control from Earth. There is no joystick in Houston that can steer your ship around hazards or manually point your cameras at a sudden flare on Proxima. By the time anyone on Earth even knows the flare happened, it's old news. Your ship has to make almost all operational decisions locally. Navigation tweaks, fault responses, even how to schedule science observations and when to enter safe mode. Earth's role becomes more like long-term strategy and software updates than mission control in the moment. Early in the flight, when you're still near the solar system and light time is hours, ground teams can help tune systems and diagnose odd behaviour. Later, especially near Proxima, your onboard autonomy is effectively the captain, and that's assuming Earth can hear you clearly in the first place across that distance. Any radio or laser signal you send doesn't stay as a tight bullet forever. It spreads out. Think of your transmission as a bubble expanding through space. By the time it reaches Earth, that bubble has a radius of 4.24 light years. The energy you pumped in is now spread across a giant spherical surface. The intensity drops with the square of the distance. Double the distance, quarter the intensity. At Proxima's distance, the signal is incredibly faint compared to when it left. That means you have 3 basic levers: how much power you put into the signal, how good your antennas or optics are at focusing and receiving it, and how clever your encoding is. On Earth today, NASA's Deep Space Network uses 70-meter radio dishes to talk to probes more than 150 astronomical units away, over 22 billion kilometers, roughly 14 billion miles. Those dishes can pull feeble signals out of the noise by integrating over time and using good error-correcting codes. Scale that up. By the time we're ready for Proxima, ground arrays can be bigger, more numerous, and more sensitive. On your ship, you can afford high-gain antennas, stable pointing, and powerful transmitters, at least for limited periods when your power budget allows it. You won't stream 4K video in real time, but you can dribble back high-value science at painfully low but still meaningful bit rates. Then there's the question of how you send. Radio or laser? Radio waves are familiar and robust. They spread more. So you lose power, but they are more forgiving. If your pointing is off by a bit, Earth still sits somewhere inside the wider beam. Radio can punch through some dust and is less sensitive to small alignment errors or slight mismodeling of your position. Lasers, on the other hand, can be focused into extremely narrow beams. That means, for a given transmitter power, you can deliver a much stronger signal to a tiny spot at Earth and achieve much higher data rates. The cost is precision. A tiny angular error in pointing can cause your beam to miss Earth by billions of kilometers by the time it has travelled 4.24 light years. Beam spread, ship motion, and uncertainty in exact alignment all work against you. In practice, you probably use both. Radio handles routine status beacons, health checks, and backup communication. It's always on, low rate, and hard to lose entirely. Lasers are reserved for scheduled data dumps when geometry and power budgets line up. The ship knows where Earth will be in the sky years in advance, aims extremely carefully, and blasts a high-rate stream of compressed science data and logs. On board, that means your communication system is not just a transmitter and antenna. It's a sophisticated planning and pointing system. It tracks the relative motion of Earth, the Sun, and Proxima. It calculates when Earth is visible and when it's blocked or too close to the Sun's glare. It slews optics with insane precision, corrects for ship vibrations, and maybe even uses guide stars or beacons to lock the beam. Now look at the software layer. You're not using the normal idea of a network where packets zip around in milliseconds and you expect quick acknowledgements. You're building a delay-tolerant network. In this kind of system, you assume that connections will be intermittent and that delays will be huge. Packets might take months or years to reach their destination. Your ship's computers cache data locally, tag it with metadata about importance and deadlines, and hold it until a good transmission window opens. When they get a chance, they send queued data in bursts, prioritizing critical science, health telemetry, and navigation updates. On Earth, ground systems do the same in reverse. They bundle software patches, new instructions, and updated models into packages that can tolerate long delays and possible losses. If some packets don't get through, the protocol can request retransmissions or reconstruct missing pieces from redundancy. NASA has already tested early versions of these ideas between Earth and the ISS. For Proxima, you stretch that concept to its limit. Power and bandwidth budgets enforce hard choices. Your reactors and batteries can only feed so much power into the comm system without starving life support or propulsion. Your downlink capacity may be measured in kilobits per second or less, so the ship has to decide what is worth sending. Raw high-res images might be processed on board into compressed summaries or feature maps. Not every sensor can stream continuously. Some instruments may never send their full datasets home, only key extracts. Those choices make the final point very clear. To Earth, the physical ship almost stops mattering once it leaves. What counts is the information pipeline. The actual atoms that make up the hull, the crew, and the engines are important locally. They keep the mission alive and moving. But for everyone back home, the only thing that ever arrives is data, spectra of Proxima B's atmosphere, detailed measurements of interstellar plasma, timing logs that test relativity, images of flares tearing across Proxima's surface, maps of possible oceans or bare rock. All of the energy, risk, and time are poured into producing a few gigabytes or maybe terabytes of clean, well-calibrated information that couldn't be gathered any other way. That data will either confirm that planets around red dwarfs can hold atmospheres and maybe life, or it will show that they get stripped and sterilized. It will refine our models of the heliosphere, interstellar medium, and high-speed travel. It might reveal tiny cracks in our physical theories, or show that they hold up even out there. In other words, from Earth's perspective, the Starship is really a very slow, very distant data generator. You're not just moving a vehicle to another star, you're turning decades of engineering and human risk into a stream of bits that could rewrite textbooks. But there's a brutal catch lurking right after that. All this communication, all this data, only matters if you can actually slow down enough at Proxima to do more than streak past in a blur. Accelerating to a fraction of light speed is one nightmare, getting rid of that speed without destroying the ship is another. So the next challenge hits directly. If it took civilization-scale energy to speed you up, how do you slam on the brakes at Proxima without turning your mission into a one-shot flyby that's over in a few hours? Here's the catch you cannot dodge. Getting up to a huge fraction of light speed is only half the job. You have to get rid of that speed again near Proxima, or your mission is just a blink and you miss it flyby. All the energy you dumped into the ship to accelerate it becomes kinetic energy, the energy of motion. When you slow down, that energy has to go somewhere. If you used a certain amount of propellant and reactor power to speed up, you should expect to spend a similar amount to slow down, unless you can lean on the environment as a giant brake. If you refuse to pay that bill, you hit Proxima's system doing something like 0.1 or 0.2 times light speed, cross the whole thing in hours or less, and then you are gone into deep space again with no way to turn around. So the first hard question is simple. Do you carry all the fuel you need to stop, or do you trust the target star to help you slow down? One straightforward option is to split your propellant and power budget, half for acceleration, half for braking. You burn hard near the sun, coast, then flip the ship around and burn just as hard in reverse as you approach Proxima. That keeps the physics clean. Your drive works the same way both times. Your mission profile is symmetric, but the trade is brutal. Fuel is mass. If you carry twice as much propellant, your starting mass goes up. That means your engines have to work harder to reach the same cruise speed, or you accept a slower ship and longer trip. Tanks get bigger. Structures get heavier to hold those tanks under thrust. Shielding and radiators scale with the overall size. The whole design balloons. The alternative is to treat Proxima and the space around it as part of your braking system. Instead of hauling all the fuel to cancel your speed, you try to lean on the star's wind, its magnetic field and its light to slowly bleed off your motion over tens of astronomical units. The leading idea here is the magnetic sail, or magsail. Picture a huge loop of superconducting cable stretched out around your ship, maybe tens or hundreds of kilometers across. You run a strong electric current through it, which generates a magnetic field extending far into space. As charged particles in Proxima's stellar wind and surrounding plasma flow past, they feel that field and get deflected. Pushing on that magnetic bubble pushes back on your ship, acting like a drag parachute in space. In principle, you could enter the outer parts of the Proxima system still moving fast, deploy the mag sail, and then let the interaction with the star's plasma slowly pull your speed down over a distance of many astronomical units. You don't burn propellant to get that drag, you ride the star's environment. In practice, this is nasty to engineer. The loop has to be enormous but extremely light. It must deploy and hold its shape in a high-speed plasma flow. The current must stay stable for months or years, and the deceleration you get is gentle. You may need to start braking far from Proxima, long before you reach the inner planets, and accept years of slow deceleration to avoid crushing the crew with high G-forces. Still, if it works, every meter per second of speed you shave off with a mag sail is fuel you did not have to launch from Earth. Can you also use Proxima's light itself as part of your brake? Light carries momentum. When photons hit a reflective surface, they push on it. A light sail that was used for outbound acceleration could, in theory, be flipped around and used backwards as you approach Proxima. Starlight from ahead would hit the sail and slow you down. If Proxima had powerful lasers pointed outward, or if you had left a beaming system parked there on an earlier mission, that effect could be boosted. But here's the limitation. Proxima is dim. Its total light output is less than 1% of the Sun's. Its habitable zone is very close in, just a few percent of the Earth-Sun distance. The radiation pressure on a sail at that distance is not nothing, but for a heavy, crewed starship it is small compared to the kinetic energy you need to dump. For tiny gram-scale probes, starlight and star-based lasers could be a major braking method. For a multi-thousand-ton ship, photonic braking ends up as a helpful assist, not the main solution. So you might carry a large sail anyway, using it first with a laser array near Earth to accelerate, then with Proxima's light to help brake. But you still expect to rely on mag sails, onboard engines, or both to do most of the work. If you're used to gravity assists with Jupiter and Saturn, giving huge boosts to small probes, you might wonder, can you just sling around Proxima and its planets to kill speed? Gravity assists depend on massive bodies. In our solar system, Jupiter is the main workhorse because it has about 300 times Earth's mass. Swing by in the right direction, and you can trade some of Jupiter's orbital energy for a big change in your speed relative to the Sun. Proxima itself is low mass compared to the Sun, and its planets, as far as we know, are roughly Earth to super-Earth size. There is no local equivalent of a Jupiter or a hot gas giant that can give you a huge energy change in one pass. You can still use smaller planets to tweak your trajectory and trim some speed, but you're not going to drop from 0.2c to orbital velocity with a couple of clever flybys. The system is simply too small to do that kind of heavy lifting for you. So orbital mechanics helps with fine-tuning, not with solving the core braking problem. You still need engines or sails doing most of the deceleration. Proxima's gravity can guide you, not save you from paying the energy bill. That leads to the uncomfortable fallback plan. What if you decide not to brake at all? A pure flyby mission accepts that the ship will never slow to match Proxima's system. You arrive at, say, 0.2 times light speed. At that speed, crossing one astronomical unit, the Earth-Sun distance, takes around 40 minutes. The entire interesting region around Proxima, from the star out past Proxima B's orbit and maybe the outer planets, spans maybe a fraction of an astronomical unit you blaze through in a few hours. In that scenario, every observation is pre-programmed. Long before arrival, while still years away, you simulate the exact geometry of the encounter, where the planets will be, how the ship will pass, which instruments point where and when. You release swarms of tiny subprobes early, each with its own cameras and spectrometers, fanning out across different parts of the system. When the moment comes, there is no time to react. Sensors just run their scripts at high frame rates and dump everything to onboard storage. From Earth's point of view, you still get incredible data. Close-up spectra of Proxima B's atmosphere, high-resolution snapshots of any moons or rings you happen to cross, detailed readings of the star's magnetic field and flare environment from inside the system. But you never orbit anything, never land, never stay. It's one pass and you are gone. So your mission choice becomes a sharp fork. Either you spend a lot more mass and engineering on braking systems, mag sails, huge fuel reserves, complex engines, to slow down and stay in Proxima's neighbourhood, or you accept a quick flyby with strict limits on what you can study. If you choose to stop, you pay a massive price in ship complexity and launch mass, but you gain the chance to put probes in orbit, land on Proxima B and watch the system evolve over years. If you choose the flyby, you keep the ship simpler and lighter, but your entire science return depends on a few hours of perfect timing after decades of travel. And if you do manage to slow down successfully, you face a different kind of challenge. Now that you're finally moving slowly relative to Proxima B, what can you actually see, measure, and touch in this alien red dwarf system that just consumed a big slice of humanity's effort? You put in decades of work and half a lifetime of travel to reach Proxima. When you finally slow down and look out the window, what do you actually see that you could never see from Earth? From Earth, Proxima B is mostly an indirect signal. It shows up as a tiny wobble in Proxima Centauri's spectrum, maybe as a barely visible dot in the best future telescopes. Out here, that changes. Your instruments can actually resolve the planet as a disk, not just a hint. You track how its brightness changes as it orbits, building what's called a phase curve, how bright it looks at different angles, the same way Venus looks brighter in our sky at certain phases. You also measure its thermal emission directly in infrared. That tells you how hot the day side is, how cold the night side is, and how much heat is being moved around. From that you get hard numbers, the planet's albedo, how much light it reflects, and the actual temperature contrast between day and night. No more relying only on models and rough assumptions. You can say, the day side runs at roughly this many degrees Celsius or Fahrenheit, the night side at that many, and the boundary zone behaves like this. Once you know the basic brightness and temperature pattern, the next question is immediate and critical. Is there really an atmosphere there? And if yes, what kind of atmosphere survives under Proxima's flares? To answer that, you use spectroscopy as your main weapon. You take the light from Proxima B, either starlight passing through its air when it crosses in front of the star, or light reflecting off its surface and clouds, and split it into its component colours down to very fine detail. Different molecules absorb specific wavelengths. Water vapour, carbon dioxide, methane, oxygen, ozone, nitrogen compounds. Each leaves its own fingerprint. You scan for those fingerprints. If you see strong water vapour lines, that hints at active water in the atmosphere, maybe even oceans. Carbon dioxide tells you about greenhouse warming. Methane and other reducing gases can come from geology or biology. Oxygen and ozone are especially interesting. On Earth, our high oxygen level and protective ozone layer are tied to life. If you see a robust oxygen-ozone signature together with reducing gases like methane or nitrous oxide, far from what you'd expect from pure chemistry, that's a possible biosignature. On the other hand, you might see something very different, a thin, dry atmosphere low in heavier molecules, or almost nothing at all. That would support the idea that Proxima's repeated flares and harsh stellar wind have stripped the planet's air over billions of years. A bare rock with trace gas would say, clearly, that this habitable zone is only habitable on paper. So you find out whether Proxima B is breathing in any meaningful sense. But even if it has air, you still need to know what kind of weather system exists on a world that may never see a true sunrise or sunset. If Proxima B is tidally locked, and all the tidal math says it probably is, one hemisphere faces Proxima permanently and one never does. That means one side is always day, one side always night. Climate models predict that such a world could form a huge, possibly permanent storm right under the star on the day side, with air rising there flowing toward the night side high in the atmosphere, cooling and sinking in the dark, then rushing back along the surface. Your instruments can test these ideas directly. Infrared maps show you how heat is distributed. Is there a sharp hotspot under the star, or is the warmth smeared around to the night side? You can use radio occultations, watching how radio signals bend and fade as they pass behind the planet through its air, to learn about temperature and density at different altitudes. If you're ambitious, you might drop in situ probes, small entry vehicles that dive into the atmosphere, deploy parachutes, and send back pressure, temperature, wind speed, and chemical readings until they fail. You pay special attention to the terminator zone, the thin ring between day and night. Models say that if there is any truly comfortable region at the surface, it may be there, not frying under direct starlight, not frozen in permanent darkness. Your data will tell you if that line is a band of clouds and moderate temperatures, or a narrow, violent weather front where hot and cold air crash together. But all of this, air, clouds, storms, lives or dies under one thing: how the planet's own magnetic field stands up against Proxima's violence. Proxima Centauri is a flare star. Space telescopes have already seen it unleash superflares far stronger than typical solar flares. Close planets get hit by huge bursts of X-rays, ultraviolet light, and high-energy particles. Your ship, now only a few million kilometers or so away, can watch those flares from the inside. You record how often they happen, how long they last, how intense the particle storms are, and how the local plasma and magnetic fields react. At the same time, you probe Proxima B's magnetosphere if it has one. You look for radio emissions and charged particle belts that signal a magnetic field trapping particles, like Earth's Van Allen belts. You measure how the incoming stellar wind is deflected or not deflected around the planet. A strong planetary field can act like a shield, steering many charged particles around the atmosphere. A weak or absent field leaves the air open to direct stripping, especially over billions of years. If you see a strong magnetosphere and a thick atmosphere under heavy flare conditions, that says red dwarf planets can protect themselves. If you see a weak field and a thin or missing atmosphere under the same conditions, that supports the idea that most such worlds are slowly cooked and eroded into bare rocks. If all of that still leaves questions, you go one step further. You send hardware down to the surface. If your braking and orbital insertion worked, and you have enough fuel and time, you can put landers on Proxima B. These are not simple machines. They must survive entry through an unknown atmosphere, or a direct descent to vacuum if no air exists. They need power sources that work under a red dwarf sky. Once they touch down, they drill into soil or ice, sniff gases coming off the ground, and send back high-resolution images and spectra. They look for liquid water, lakes, oceans, or underground reservoirs. They analyze minerals to see if the crust is basaltic like Earth's ocean floor, or dominated by other rock types. They check for weathering that suggests long-term interaction with liquid water, like certain clays or sediment layers. If there's an ocean, they sample its chemistry if possible. If the world is desiccated, they map how and where volatiles like water and carbon dioxide are locked away, if they exist at all. Even if every test screamed dead world, that answer matters. It tells you whether red dwarf habitable zones can stay stable for the billions of years life needs to get going, or whether flares and stellar wind usually erase atmospheres and oceans before biology ever gets a chance. A single well-studied Proxima B could shift the odds on tens of billions of other red dwarf planets across the galaxy. So by the time you finish your first few years in the Proxima system, you will know whether this closest second Earth candidate is even remotely Earth-like, or just a harsh, locked rock under a hostile red sun. But even that is not the end of the story, because whatever you find here, life, no life, scorched rock, or something stronger, will feed straight back into how our entire civilization thinks about starflight, technology, and its own future. The next step in the journey is no longer just about Proxima. It's about what this single mission does to the way humanity builds, governs, and imagines everything that comes after. How big does one mission have to be before it stops being a mission and starts being a test of your entire civilization? Apollo put 12 people on the moon over a few intense years. The money, the factories, and the media focus were huge for their time, but they were still working on a decade-scale project. A Proxima mission doesn't fit in that box at all. You're looking at decades of design and ground testing, then a multi-decade cruise, then more decades of data analysis and follow-on missions. The total energy you burn, the kilograms of hardware you launch, the number of people whose careers are tied to it, all of that dwarfs anything humans have ever done. You're building heavy-lift rockets, orbital shipyards, fusion-class drives, or multi-gigawatt laser arrays, long-duration habitats, and planetary-scale communication networks. You're committing a noticeable slice of global industry and scientific talent for half a century or more. If it works, this becomes the reference point. Future civilizations, human or not, will look back and say, that is what it looks like when a species first reaches beyond its own star. Apollo stays important as the first step off the planet, but Proxima becomes the moment you prove you can operate on star-to-star scales, not just planet to planet. But this isn't only about building big hardware. You're also doing something else in the background. You are stressing physics itself in ways we've never done before. All through the trip, every part of fundamental physics is under pressure. Special relativity guides your navigation and timing over light years. General relativity creeps in as you thread gravity assists and measure tiny time differences in your onboard clocks. Plasma physics runs the show around your engines, your mag sails, and your interactions with the heliosphere and interstellar medium. High-energy particle physics sets the rules for radiation damage, shielding, and cosmic ray behavior. Right now, we've tested our theories mostly in particle accelerators, around Earth and inside the solar system. A Proxima mission opens a completely new regime, a macroscopic object, your whole ship, travelling for decades at a fixed fraction of light speed through varying environments, with synchronized clocks and well-calibrated instruments logging every detail. If there is any small crack in our current theories, a tiny violation of relativity's symmetries, an unexpected shift in cosmic ray spectra, a plasma instability that doesn't match models, it's more likely to show up on a mission like this than in another few years of lab work. You didn't launch this ship to hunt for new physics, but you might end up forcing textbooks to change anyway just by comparing predictions with what actually happened. And to even get that far, you've already had to build entire industries on Earth that don't exist yet. You can't develop propulsion for a Proxima ship without pushing energy tech to a new level. That likely means compact, reliable nuclear fission reactors or fusion systems that make today's plants look crude. You need ultra-light, high-strength materials for hulls, sails, and shields. You need closed-loop recycling for air, water, and materials that actually works for decades, not just months. You need autonomous manufacturing plants to print, machine, and assemble components both on Earth and in orbit. The side effect is that these same technologies feed straight back into life at home. Better reactors and storage help with clean power and grid stability. Closed-loop recycling helps cities and remote bases handle waste and shortages. Autonomous factories and repair robots make industrial systems more resilient and less labour-intensive. Long-duration habitat design helps with everything from underwater stations to disaster-resistant housing. So that mission stops looking like a luxury science project and starts looking like a pressure cooker that forces your civilization to level up. If you actually commit to going to Proxima, the technical demands push you into solving problems that matter on Earth too. Climate resilience, energy security, resource limits. But technology alone doesn't carry a mission this long. The way you think about time has to change as well. Most companies think in quarters or, at best, a handful of years. A Proxima mission is locked in on half-century scales. From early design to late-stage data, that's 1 or 2 human lifetimes. No normal budget cycle or election rhythm is stable enough to carry it from start to finish. To make it real, you need governance structures that can survive leadership changes, economic swings, and public mood shifts. That probably means international consortia with binding treaties, protected funding streams, and clear long-term mandates. It may mean dedicated agencies or alliances whose whole purpose is deep time projects, insulated as much as possible from day-to-day battles. Public psychology has to adjust too. People have to accept that they will pay taxes, vote, and live their lives under a project that may not report its final results until after they are gone. That's a very different mindset from "we'll see results next term." You start to think more like a species planning across generations, not a group of separate countries planning around elections. And that raises one final hard point. What if you do all of this and the mission still fails? Maybe the ship suffers a critical failure halfway and can't brake. Maybe the magsail doesn't work as expected. Maybe the crew runs into a health problem biology didn't predict. Maybe you get there, slow down, and find Proxima B is absolutely dead. No atmosphere, no water, nothing but flares and rock. On a normal mission, that's called failure and written off. At Proxima scales, it's different. The attempt itself has already forced breakthroughs in propulsion, power, materials, life support, and governance. Thousands of engineers and scientists have trained up on problems they would never have tackled otherwise. The public has spent decades thinking about stars, distances, and long-term plans. You still get data, how your hardware aid, how your closed ecosystem performed, where your models of the heliosphere and interstellar medium were wrong. You get social lessons on what kind of agreements and institutions survived the long haul and which ones didn't. You get psychological data on what long-term isolation does to people and what helped them stay functional. So even a ship that dies in interstellar space, or a mission that only proves Proxima B is sterile, changes the baseline for every future effort. It tells the next generation exactly what not to do, what to overbuild, what to simplify, and where the real unknowns still are. And once you've done it once you've proved that you can coordinate this much energy, time and attention around a single star, the obvious question appears, does it stop at Proxima, or does this become the opening move in a much bigger expansion? So after you've spent half a century getting to one star, do you call it done, or do you treat that as the first time you finally know what you're doing? Once you've actually flown a Proxima mission, you've solved the hardest part, the first time. You will have working answers, not perfect but real, for propulsion, shielding, life support, navigation, and long-distance communication. You'll know which materials held up over decades, which life support loop stayed stable, what kind of engine cycle was manageable, and which design mistakes nearly killed the mission. At that point, there is no good reason to stop at one shot. You start building a launch cadence. The same way our first lunar missions were bespoke and slow, and then rockets and procedures became standard, interstellar hardware starts to move from one-off masterpiece to version 2, version 3. You reuse major blocks, drive modules, reactor designs, habitat rings, comm systems, and software stacks. You toughen them where Proxima data showed weak points. You strip out overbuilt parts that never got stressed. Then you line up new targets: Alpha, Centauri A and B, Barnard Star, TRAPPIST-1, other nearby systems with promising planets. Some missions are crude, many are not. At 0.1c, a probe reaching a star 10 light-years away in about a century of Earth time is suddenly a practical plan, not a fantasy. So the transition is clear. Proxima is a prototype. After that, stars become a list. That leads to a sharper next step. Once you can send machines to other stars reliably, do you let those machines start building more machines without you? Full self-replicating probes, von Neumann probes, are still theoretical and loaded with ethical worries. They would mine local asteroids, build copies of themselves, and spread out potentially without human control. That's a scenario people argue about for good reason. But you don't have to go all the way to full self-replication to get a big change. You can design probes that do partial bootstrapping. A first-generation craft arrives in a new system, mines local rock and ice for reactions of mass or structure, and builds simple, non-replicating follow-on vehicles. Landers, orbiters, maybe a return data relay. It might even assemble a next-generation interstellar probe under strict constraints, with tight rules baked into hardware and software so it cannot grow unchecked. Run that logic for long enough, at about 0.1 C, and the timescale to touch the entire Milky Way with machines is surprisingly short in galactic terms. A few million years, still far longer than human history so far, but a blink compared to the galaxy's age. On those scales, sending out unmanned scouts to every interesting star stops looking ridiculous and starts looking like a long-term surveying plan. That raises the real payoff. What do you actually want all these missions to build up to? Right now, our data on planets around other stars is coarse. We often know the orbital period, a rough radius or minimum mass, and maybe a bulk density. In a few special cases, we have hints of atmospheric composition. That's not enough to say this is a good place for life, with any real confidence. Every interstellar mission you add fills in more of that picture. Probes and ships at Proxima, Alpha Centauri, TRAPPIST-1, Barnard Star, and further out send back high-resolution atmospheric spectra, detailed climate patterns, and surface geology. Over centuries, you go from vague catalogues to a real 3D map. Which systems have thick atmospheres, which have oceans, which are tidally locked but stable, which are dead and dry, which are toxic but terraformable. The result is a map of habitable real estate, not theoretical habitable zones. Green dots, genuinely temperate with stable air and water. Yellow, marginal with serious engineering needed. Red, permanently hostile, empty, no real planets to work with. Proxima Centauri becomes the first pin in that map. Whether it's green, yellow or red, not the whole story. Underneath that, you're chasing one question that all of this feeds into. When you finally start checking real alien worlds directly, do you see signs of life or do you see nothing? Your instruments are tuned for that. On each world, they look for atmosphere chemistry that makes no sense without ongoing processes. Oxygen with methane, or other gases that should erase each other quickly if something isn't constantly replenishing them. They look at isotopic ratios in rocks that life can distort. They look for complex organic molecules, where geology alone has trouble making them in such abundance. In some cases, landers or ocean probes go hunting for direct traces. Pigments, simple cells, repeating structures that scream organized chemistry instead of random sludge. You might find biosignatures on many worlds. A red dwarf system with a hazy methane-rich sky and trace oxygen. A sun-like star with a planet that smells chemically like early Earth. Small icy moons with subsurface oceans rich in organics and energy sources. That points to life being common, says, given time and the right conditions, chemistry almost wants to wake up. Or you might hit planet after planet and find only sterile landscapes. Atmospheres that make perfect chemical sense with no life. Oceans that are salty and still with no signs of metabolism. Surfaces scarred by impacts and tectonics, but no fossils, no trace gases, no subtle hints. That picture is just as shocking in a different way. It means Earth might be very rare, maybe unique, in any reachable volume of space. In both cases, your Proxima flight marks a break. If life is common, then this mission is part of the early stage of joining a crowded galaxy. If life is rare, then this is the moment one fragile biosphere started to reach out into a mostly empty universe and change it. Once that kind of exploration is underway, the last shift might be the biggest. Starflight stops being the impossible thing and becomes background. Today, a mission to Mars still feels like a massive, historic event. A mission to another star feels almost beyond belief. But after a few generations of running Proxima-class projects, a pattern sets in. Launch windows, build cycles, training pipelines and funding lines become standardized. Ship classes evolve the way airliners did. Big upgrades every few decades, minor refits in between. The first time you do 0.1 C is a headline. The 10th time is a normal engineering milestone. Psychologically, the size of your home changes. Instead of thinking solar system as the outer edge of what's real, people grow up with maps of the local 100 light years. Which systems have outposts which are understudy, which are next on the launch schedule. A mission to Proxima looks huge historically because it is the first. A few centuries later, It looks like early aviation, clumsy and brave but primitive compared to what followed. So the journey to Proxima Centauri is not just a one-off epic. It is, if you choose to keep going, the pilot episode. It establishes the characters, propulsion, shielding, life support, autonomy, biology. It proves the setting, interstellar space, is manageable, and it sets up a series, not fantasy, but a long, grinding, real sequence of missions that over time open up the galaxy around you. The only real question is whether you ever decide to aim that hard at another star in the first place, or stay home, looking up, knowing that the path is possible and waiting to see who takes it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.